Dear students, welcome to the course of VLSI Circuits and Systems. Today's topic, rise and fall time estimation. Rise time estimation and fall time estimation. In our previous topics, continuously we are focusing on basic circuit concepts. As a part of basic circuit concepts, we have started with the sheet resistance of layers and then with the capacitance of layers, area capacitance of layers we call it as, then followed by delay unit, then followed by inverter delays. So all are continuous topics where sheet resistance and capacitance, area capacitance are the basic circuit concepts. Based on this we derive delay unit, and based on the delay unit we have done inverter delays. Now based on these we are going to learn one more concept called rise time and fall time estimation of a CMOS inverter. Right. After completion of this lecture, you will be able to compute the expressions for rise time and fall time of a CMOS inverter. Going into the details, as we have learned in our previous topic that the delay unit, otherwise called as time constant, that is given by RC for a given standard unit of capacitance driven through, that is charged through, an N-channel MOS transistor, we have derived its time constant as a product of the sheet resistance multiplied by a standard unit of capacitance, which for a 5 micrometer technology has been done as sheet resistance standard value as 10 power 4 and standard unit of capacitance as 0.01, and the delay time has resulted as 0.1 nanoseconds. Similarly, for 2 micrometer technology, the sheet resistance and area capacitance, the product has resulted in delay unit 0.064 nanoseconds. And for 1.2 micrometer technology, the sheet resistance and area capacitance product has resulted in the delay unit as 0.046 nanoseconds. So with these few details, we have done with the inverter delays of NMOS and CMOS elaborately we have discussed in the previous topic, where this portion of an NMOS inverter, which is in which the input is transition is making a transition from 0 to 1, so definitely the pull down transistor of this NMOS inverter will be switched on, so and there will be a discharging path for the standard unit of capacitance. So the discharge path MOS transistor will be giving a sheet resistance of 10 power 4. So 10 power 4 and the sheet standard unit of capacitance put together, it is considered as single delay unit. The same thing when the output of this NMOS transistor is going from high to low, so this is driving this NMOS inverter. So in this case the pull-up device will be on, so standard unit of capacitance will be charging towards the supply, resulting in a delay unit of 4 tau. Why? Because ZPU by ZPD ratio of an NMOS inverter is 4:1. So put together total inverter delay is 5 tau. So in general, for an NMOS inverters, pair of similar NMOS inverters, inverter delay can be generalized as 1 plus ZPU by ZPD into tau. And taking this into consideration, in similar lines, we have made the CMOS inverter analysis also. Like for a CMOS inverter, pull up will be PMOS and pull down will be NMOS. So NMOS will be 10 power 4 kilo ohms only for on transistor, but whereas PMOS that will be 2.5 into 10 power 4 kilo ohms, 2.5 times the resistance of pull down. So in this case also, if your input is going from logic 0 to logic 1, your standard unit of capacitance is 2 times actually. Why? Because both the gates are connected, both the transistor gates are connected in order to form the input of a CMOS inverter. So this standard unit of capacitance multiplied with sheet resistance is tau, and this 2 is making 2 tau. Similarly here, this standard unit of capacitance and this 10 power 4 will make tau, whereas 2 into 2.5 makes it 5 tau. So put together the total inverter delay is 7 tau in the case of CMOS, whereas in the case of NMOS that is 5 tau what we have seen, that is 1 tau plus 2 tau, 4 tau, right? With these details, let us have a rise time estimation, rise or fall time. So when the output will be rising, that is going from 0 to 1. So when it will go from 0 to 1 means when input is going from 1 to 0. So when your input is going from 1 to 0, in your CMOS inverter, pull down is NMOS and pull up is PMOS. This is VDD and this is the ground, input and output. So in this case, when your input is going from 1 to 0, NMOS will be in off state and PMOS will be in on state. So P device stays in saturation for the entire charging period. So here the output we have a capacitive load, charging period of the load capacitor. So in this case, the saturation current of P device, as we know, the expression is given by beta times VGS minus VT whole square by 2, general equation. So this current charges the capacitor CL. So this is the load capacitor. Since its magnitude is approximately constant, so this magnitude beta is constant, VGS is constant, VTP is constant. So this current is constant which is charging the capacitor CL. So in this case, the voltage across the capacitor, that is V out, actually in general is given by the formula 1 by C integral IDT. But the current, that is IDSP, is constant as we have discussed now. So this has changed to IDSP by CL into T. So when you rearrange the above terms, this T can be rewritten as 2CL, or substituting IDSP in this equation, 2CL V out by beta times VGS minus VT whole square. So this is clear. So once we have made the output voltage equation and rearrange the terms to get T, we now assume T to be tau R, that is rise time, when our output is going to reach its final value, that is VDD. So in this case, T becomes tau R and V out becomes VDD. And substituting the typical value of VTP as 0.2 times VDD, rise time is represented as, calculated as 3CL divided by beta P VDD. CL is the load capacitance, beta P is K into W by L of a P transistor, and VDD is the supply voltage. Hope this is clear, rise time expression. So in similar lines of fall time estimation, there is no requirement of any derivation. Directly you can say fall time will be when your output is going from 1 to 0. When this will happen for an inverter? When your input is 0 to 1. When your input is 0 to 1, your NMOS will be on and PMOS will be off. This is off. So here the capacitor discharges through this transistor to a current of IDSL. So in similar lines, we can say the fall time is equal to 3 into load capacitance divided by beta N into VDD. Hope this is clear. So based on the rise time and fall time estimation topic, there are few lecture level questions which we will be discussing in our classroom. That's all for this topic. Thank you. Happy learning.